So, yeah, ready? Okay. All right. So, welcome to seminar summer course series number 6. My name is Burak Akin. I'm a postdoc in Peter Benedetti's lab. Today, I'm going to talk about physiological confounds in fMRI. It could be the name physiological noise or physiological fluctuations, depending on the context that you're working on. Maybe just to start with that. So should we say confounds or noise, or should we say like neuronal activity or brain activity? It is kind of it's a mixed things. Depends on what you're interested in the brain science. Actually, like I want to ask people in here, like, what is the definition of the noise for you? Is it something that doesn't fit the model? Is it something that, if you're working on task fMRI, something that non-task related variability, or something just looks like this? If you're familiar with old CRT TVs, like, you know, a bunch of salt and pepper noise. So it could be depending on what you're working on. Like in fMRI, we work on time series, look like this, but we tend to like things like smooth changing, like up and down, that we can understand, read, pleasing to eye. But to better understand that, we need to look at what we are recording with the fMRI. So functional MRI is a technique that you're measuring the deoxygenated hemoglobin, as you probably all know from the previous lectures too. And this is a coupled effect called blood oxygenation level dependency. And this is a very complicated thing to understand, actually. If you have a task in a certain brain area and the neuron starts to consume some oxygen, you see a dotted line there as a consumption. And then with the task, they start to use oxygen, and then around become deoxygenated. That's actually what we're measuring. But it reaches a certain level, then it says, hey, this is like not enough oxygen. We need to supply oxygen to the tissues. It's an alert, and the blood started to flow because it just triggers a local blood flow response, which is shown in like a thin line flow, and then it washes all the deoxygenated hemoglobin. So this creates like this kind of a curve, and then it goes back all the way back to the baseline. And by using this mechanism, we just, you know, ask subject to do like finger tapping or visual checkerboard and see this kind of patterns are matching with our task. So yeah, it is an indirect measurement. There's like neuronal activity. There are like two things. One is oxygenation around the tissue, and the other is the blood flow that clears out. And if you closely look at those things, oxygenation is closely related with the respiration in general, regardless of neuronal activity or not, because we maintain to stay alive. And also, blood flow is highly related with the heart rate, your cardiac activity. So today, I will be talking about those two. To start with a little bit history, I will take you like a century ago. This guy is a physiologist from Italy, Angelo Mosso, and he was interested in the blood flow in the brain. And then at that time, as you can appreciate, there are no MRI machines. He built this scale, because what he thought was like, you know, if I ask hard math questions, there will be more blood flowing in the brain, and the scale will be tipped over towards the brain size. But soon after, he noticed that the scale is not stable at all, because patient volunteer here is breathing, there's pulsations going on. So he decided to put a lot of sensors around. But he wants to measure how the chest going up and down. He wanted to measure how his foot here, like getting larger. So like pulsations are around the body. And then there is a rotating paper here. If the scale goes up and down, and then there's a pin, he writes some waveforms of that rolling paper. That's kind of amazing for the time of the technology, like not using helium probably no electricity there too. Yeah, and then I found this from the museum, his devices in the museum in Italy. It looks like medieval torture devices. It worked, and he measured 3 time courses there, actually sampling rate infinity because it's an analog measurement. There's no sampling. It's just continuous measurement. And as you can see, I mean, one can take out a lot of things here, like they co-fluctuate. The large oscillation at the bottom you see is the chest, inhale, out, and in. The sharp thing on the top is the pulsations, which is like cardiac. And the one in the middle he was trying to do is modulate with the task, asking questions. But he wanted to be sure that it is not changing with the others because he wants to disentangle that effect from the ongoing physiology, which was a hard thing. Even at that time, correlation coefficient was not in the place. So yeah, it's quite amazing. But back to nowadays, potential noise sources in fMRI, as you may guess, motion is the biggest challenge. Although it could be physiological or non-physiological, but there are a lot of things and they're kind of overlapping and interacting with each other too. So you breathe in, you change the magnetic field in the area, it changes your signal. But if you breathe in, you get oxygen in the blood, and then it also changes your activity levels. Also, there are like, vascular pulsations, which I will show in the following slides. But things are more complicated than that. So like, it's hard to summarize in subtitles, but if you say noise, maybe we shouldn't say noise, but yeah, let's say noise, could be hardware related. So even if you put a jar of oil, non-living thing, if it's hardware related, you will see that noise. For example, thermal noise. It could be physiological if you're working on living tissue, and then motion as usual. So hardware related, as I say, thermal noise, unless if you're not working with the absolute zero, freezing cold, if you measure the same spot, there will be some perturbation over it because of the physics of the nature of the MRI. And the common thing is the scanner drift. Last lecture, Paul Taylor mentioned a little bit about it. It is a common thing that needs to be removed. I will also mention in the upcoming slides. And the motion. Motion could be, as I said, like sourced by anything, either respiration, cardiac, voluntarily, involuntarily. If you fall asleep, maybe your head is going to fall down slowly, or when you wake up, you suddenly come up. So there will be a lot of motion, although the reason for the motion might be different. And then physiological. So within the physiological, we also need to look at the motion too. But the main thing is that, as I said, for the respiration, the time-locked activity, when you breathe in, oxygenation changes, and so on. And V0 field changes, the carbon dioxide and blood flow. And with the cardiac, also quite similar. And also it causes some motion too. And I will have some nice animations to show that. Next. This slide I put just to show you how things are so feedback mechanisms and complicated, like a fringe style. But I'm not going to go into detail on this. I will stick to the previous slide I will show. I showed. So in this case, like if you look at the brain with different compartments there, there's a lot of things going on there with the brain and heart interaction. So brain sends signals to heart, can change the heart rate, and heart change the amount of blood pumping into the brain. So they're kind of, there's a feedback there. But there are other components inside. For example, vasculature. And there are some vascular areas are not equal in the brain. Some areas are more vascular, some areas are not. And the total volume of the brain, as Monro-Kelly hypothesis says, like it shouldn't change. And it tries to be maintained. So if you have a really strenuous task that asks blood from the peripheries, then something should go out. And that's usually the case if you see at the bottom. If the blood volume here increases and the CSF should go out, as the brain tissue volume is not going to change. So that brings extra spice into things. Then the CSF is moving up and down too. It goes, there are like certain areas in the brain that it flushes out, they're plumbing in things. But there's also a pressure component of it. The brain tries to maintain the pressure, and maybe, you know, in certain diseases like hydrocephalus, if it's not plumbing out, then it will cause brain to increase volume, the skull. Yeah, and there's also other things like autonomical emotions, like we usually disregard those kind of things, but you know, there's emotional cycles and autonomous system, parasympathetic and sympathetic flows, and these are all changing these parameters, and not even mentioning the hormonal connections. So how do we measure the physiological signals? For instance, cardiac activity. That's alone, if you think like without MRI machine, is a task. Like heart is an electrical activity that just creates some currents around the body, and then here you see the Eindhoven, kind of a debunk experiment he was doing there. He just put his hands and leg in a salty water and then tries to measure his activity with the heart. It actually brings the idea of Eindhoven triangle, because like the dipole of the heart is changing, and then you need like 3 points to just follow where it's going, and then you measure this cardiac activity. Actually, like if you have more electrodes around the body, you will have more precise measurement of it. But the thing is, inside MRI, things are different. It's a noisy environment, and luckily nowadays we have like complicated electronics. There are like filters. Like it is a tricky thing to use an electric cable inside a magnetic field. It can cause problems, and moreover, like the signal might be perturbed. But the signal in the body is very, very weak, the electrical signals, including neuronal signals, that needs to be amplified. So on the right side, you see a typical amplifier we use to measure physiology during MRI scans. And it's usually converted to optics, and depending on the transducer we use. The other thing actually makes things a little more complicated. If you measure ECG, the cardiac activity outside the scanner, you see this kind of a pattern. It's a QRS cycles, and then it goes up and down on a like nice routine. But if you go inside the scanner, because blood is conductive, these currents are perturbed. And this causes a particular problem that of peak detection, because we want to know how frequent heart is beating, so that we understand if it affects our neuronal signal. But if we cannot record that right there in the beginning, that will cause a problem. So there are ways to mitigate that. Depending on electrode, you can filter after you record. You can there are techniques for that. I'm not going to go in detail, but there's pulse oximeter, for example, is an optical measurement. Luckily, there's no interference on that. Probably if you went in a scanner, you saw that like it's a finger transducer that it measures the activity of the oxygenation in the fingertip. It looks like cardiac. I mean, if you look at like R to R interval, and like if you measure the second one, which is like P to P interval, they are more or less similar measurements. But the thing is, one is from the finger, one is from the heart, and there's like a delay component of it. Here is a nice animation showing that their blood is pumped to peripheries and also the brain. There's also certain time needed to go to the brain and to the finger that you measure. And that's something we need to keep in the mind. And there are some studies also showing that the difference between pulse oximeter and the electric activity of the heart could be changed if you're doing a task. So there might be some incompatibilities on that, so we need to keep it on mind. But usually this pulse oximeter is used because it's kind of noise-free or interference-free measurement. So to move along, like what are the characteristics of physiological signals? They're like, I think I will show you two. If you want to guess, you can go ahead and tell. So, for example, I'll show like two signals, like respiration and cardiac signal. Anything you can tell that is and anything in common both. Any guesses? They look very different. The interval, actually, breathing is way slower than cardiac. The heartbeat is like every second or so. Breathing is maybe 5 to 10 seconds. The thing is, they're periodic. If it goes up and down, and just there's a periodicity. So it's like, you know, heartbeats a minute, a second, like respiration is certain. Of course, there's like variation too, which is the second one. So first is a periodicity, which we can use to understand the signals in the fMRI too. And the second one is the variability. So it looks like it is continuous, but if you measure the intervals, it may change. And they may interact with each other. So talking about functional MRI after a lot of brainstorming on the physiology, and fMRI images are also not ready to do statistics on them. Like, okay, you want to see time course fMRI, you cannot correlate with your heart rate immediately. They need to be conditioned. And this is partially discussed in pre-processing lectures. It comes out of the scanner usually in this way. They're like slices of brain, and then we need to reorder them such. So we have space and time. And so we look at the time courses, and there's usually a drift like this, which causes due to scanner noise, and that needs to be corrected so that the statistical properties are ready for the temporal properties are ready for statistics. This can be named like baseline correction, trend removal, or like scanner drift removal. This is important for physiology too. And the other is like abrupt motion. Time course goes and then jumps down. It could be because you moved your head. It could be because there's a vein coming around the neurons, like this suddenly pulsated, and then the tissue is like dislocated if it's very local. And it's not necessarily at the same style in every voxel. It could be the opposite, because like if you rotate your head, the back of your head is going up and the front is going down. So this could be, we have to take that in account too. That in this case, it is nicely corrected, but it's not always easy. And it is usually named as a terminologically image alignment, registration, or motion correction. But talking about motion correction, it would be nice to have an external parameter, because we don't know how you move the hand. Of course, we have series of images. We can look if it is like dislocated, but if it is like tiny motion that is smaller than the voxel size, it would be nice to have an external measure. And in this case, I show you a marker, which is like a holographical marker that is very sensitive, like an angle dependent. And if you put it in the front of the head, and then you can have with the camera at a certain time course of it. Actually, with that, you can measure the cardiac influence, cardiac induced head motion, which is called ballistocardiographic artifact. If you happen to sleep on your prone position face down, you can feel your heartbeat sometimes on your face. This is what I'm talking about. Like the pressure of the blood just pushes your head up and down. It is very minor effect, but if you're looking for tiny activation, especially in high resolution, it is crucial to correct that too. And it is usually in the Z direction, because in the scanner we are laying on the laying down, and then just heart is pushing the blood in the Z direction. And then after those are corrected, this is kind of the QC, like quality control. Then we are ready to look at for physiological noise correction. Of course, you can do other stuff, which I'm not going to go into detail, like you can remove the skull, you can make the tissues, you can tissue-dependent signal correction, that you can look at the spectrum, and then you can smooth data if your activity is large, especially. And there are several or like many tools available. A few I will show later in the talk. Yeah.
How can you perform like this?
Oh, together with EEG tap you're asking, or is that something? It depends on the questions. Like if you are both interested temporal aspects, because like there's electrical activity, you can record with the together with the fMRI, and there's like timing. You can extract more timing information in EEG, and then look at your fMRI data, which has more special information. So you can combine those two measurement techniques, but it is more tricky because there will be more artifact correction on EEG because it's an electrical measurement too. Yeah.
So you define noise, is that synonymous with artifact? Is that the same? Or
it is hard to say at this point. I mean, there are a lot of labs studying particularly physiology. So for them, physiology is signal. They are, I mean, they just wanted to see how CSF moving in the brain in certain clinical disease, for example. For them, they want that. But for us, like if you're just doing basic cognitive or neuroscience study, you are interested more in neuronal activation. So for us, physiological signals are usually bad or unwanted or secondary signals. So in that case, yes. And in the literature, you can say like, you can see that this is a physiological noise. It is mentioned in those studies more.
so yes, there's synonymous that was thinking artifact.
Artifact and noise, not synonymous, but similar. Yeah. Hope that answered your question. There will be more, yeah. So improving temporal resolution would help because these signals are in the time correlated, and there are techniques to do that. On the left, you see an echoplanar imaging, which delivers a decent image quality, but it is rather slow because you acquire K-space, which was mentioned by Vinay 2 lectures ago, slowly line by line manner, but you can speed up that process with the expand of image quality. And then you will have a lot of volumes and time information. And then you can model differently because you start to see more fluctuations, which is potentially related with physiology. And in this case, model instead of signal plus noise could be signal plus noise plus physiological fluctuations. So like fast fMRI opens new applications areas that I'm not going to mention here, but particularly it is important like for physiological noise removal or understanding it in a better way. So in typical fMRI, we modulate the signal on and off, and there's like going up and down. That's the pattern what we are looking for the neuronal activity. So, but if you increase the temporal resolution, you start to see a lot of fluctuations around there. And if you happen to have a physiological measurement like your ECG or respiration valve during the scan, you see those are matching. So they're like time-locked activity on that. And also for cardiac too, in certain, of course, this is depending on brain region. And you can appreciate the shape is different and not necessarily it's going to be same because these waves are traveling, and then in the local area, maybe there's a vasodilation, and suddenly the waveform is different than it is recorded in the original source. Here is a nice graph I would like to show. It's kind of a classification in the frequency domain. So if you start to increase the temporal resolution, there is a a space of a frequency that we can classify those fluctuations, and then maybe potentially be careful at that areas or like filter them out. That's also possible. So if you see here, like it's like sampled up to 5 hertz. Usually in the resting state, cardiac heart rate is usually 60 BPM, which corresponds to 1 hertz, and you can see the peak, but there are harmonics of it because like there's a lot of pulsations around the heart, which is different than the 1 hertz, and you see other peaks too. And respiration usually is actually dangerously close to the task area. Oops. And there are like other cardiac components. So actually, since you have a lot of volume, you can start to create movies of it and understand how these pulsations spread all over the brain. And the fastest one will be cardiac. So obviously, it starts from the inferior part of the brain, and then it just spreads around, which follows the veins and draining veins around the brain. This you see respiration. It is slow. It's kind of you can see the breathing pattern in and out, in and out. It is all over the brain. Some regions affected more. You can see the average image here, but it's transiently all over the brain. So, and this is another graph to show that how fast you need to sample. I mean, if you're running a study that needs a good image quality, it is hard to do both. So you need to decide because you cannot hold the patient or your volunteer long inside the scanner. So you need to compromise. Either you scan fast and then you have poor image quality, or you have good image quality and then temporal resolution is bad, then you're alias those artifacts. So typical protocols TR2, TR3, and the effect we are looking, the neuronal effect, the bold effect actually, we are looking is a very low frequency. So they're all covering that. But if you're interested, those physiological signals, you need to better get higher, especially in the cardiac area. Yeah, there are ways to do that. You can only acquire one slice and then work on it if you have a hypothesis and working on a certain brain area. And you see like very rich oscillations here, and they're kind of classified in different frequencies. So yeah, you can do frequency filtering if you're interested only in respiration, or if you're interested only on cardiac. And then if you remove them, then the left will be in quotation bold. So this sources spatial temporally overlapping, and this is kind of a small animation that like imagine like the sources of circles that are like overlapping. One is oscillating very slow, 0.05 hertz kind of activity of the brain, and there's like respiration up and down, which is 0.3 hertz here, and then there's cardiac. Like if you happen to sample like 2 seconds and then look images every 2 seconds, you start to see them appearing together. But if you happen to scan faster in a certain frame, you can disentangle them in the space too. And they are, if you look at this frequency spectrum, how and which brain regions are affected, actually it partially shown in the previous video, and this is like an average, like an average image of it. So the respiration and cardiac, you can appreciate that the lower brain areas where the veins are going and a lot of CSF motion plumbing happening. But the respiratory is also changing the vascular tone and carbon dioxide. So you can see the draining vein at the back of the head too, very bright. So now comes the big question, actually, how to denoise the fMRI data. We should model the task paradigm carefully. The potential thing is like you model it such that it is not overlapping in time. Let's say this respiration, like if your task is slow, kind of sync with the respiration, it's hard to disentangle. and also measure them. Many studies just, they think they don't need measuring physiology. If they have a long paradigm enough, they can see the effect. And then if you measure them, you can regress them out. That's a potential way. So typical analysis in fMRI data, if you have the model, you can regress them out, or you can just look if it is matching with your model. So like in this case, like we observe a time course in fMRI data, here shown in time, and then we have a design matrix, which we design like kind of on and off. I show the light, I just turn it off, on and off. And then if this matches with that, and then the quality of match will be given with the value. So in this case, there's like two things. These are not physiological, but could be physiological pulsations put there. And anything that doesn't fit will be in an error. And then you need to minimize the effect. So you want to minimize the error because you want your signal to be matching with your model. So that's how you solve. And in this case, like this straight line matches with the average value, which is mean, and then the up and down value is just matching with the shape. There's still a lot not explained. So we can either populate those design metrics as much as we can, but there's also potential risk. Maybe later I will talk about, like, if you have a lot of things that you try to fit in this case, like cardiac oscillations, or then there's a potential risk of overfitting the data and mathematical problems. And here obviously, like in this case, it's a very simple case. In fMRI, you have 500,000 voxels. In this case, it looks like a carpet plot. So there's like a lot of voxels up and down, that's not necessarily matching. And if you do the same technique, like then there will be set of beta values, which will be in the order of 100,000s of 500,000. And then look, where are they matching, and then put it back to spatial domain, XYZ in this case, and then you find the activity. And then basically for physiological confounds, we need to model that and then see where they're influencing. In this case, it's a visual paradigm. Moreover, like how to denoise the fMRI data, you can just filter, even you haven't measured, like moving average filter. So on the top, you have the raw data. We know there's some perturbations on it. You can just, with the window, go smooth and move it on, which is like moving average filter. Or you model the artifact. So you have an external measure, and then you regress it, as I show in GLM. You put in the model, and then you just try to explain it. There are two main differences. So if you do moving average, you just kind of trim out those peaks. But if you do if you do moving average, you just substantially suppress everything. But if you do model, artifact modeling, you just removing those particular physiological peaks. There is a potential risk in moving average filter if your data is not enoughly sampled. In this case, you see a highly oscillating signal that is measured with the slow signal, then it will appear as a low frequency. This is called in signal processing aliasing. So if you just filter, you may filter the physiological artifact induced might not be filtered. So that's what I'm trying to say. And the other widely used technique is independent component analysis. This is like blindfolded, so I don't know what is physiology, what is signal. Maybe I don't have a task. I'm just sitting inside the, we're laying inside, I wish I was sitting. I was laying inside the scanner. That actually causes another bias because we usually do sitting daily activities, but measuring our brain in a laying position. So if you don't know the model, you don't know the signal, and then you need to look at how signals are related to each other because you don't have a model. And in that regard, ICA becomes handy. because it just solves the problem such that the distribution of the signals should be non-Gaussian, because the information theory says that if something is Gaussian, it's probably noise, but it should be non-Gaussian, like up and down. So this algorithm kind of try to make signals non-Gaussian properties. And then by doing that iteratively, it just creates components that are non-Gaussian. And these are called components. And then what you do, you sit and look, oh, this looks like a network, because I know it's a default mode network, but I know that there's an activity on occipital. So you flip through the activity patterns, and then you can just manually, okay, this is artifact, this is activity, this looks like. That's although the method itself is blind and very fast, but you need to go through, there's like manual interaction needed at the end because there's no model. So you need to know with the prior information, for instance, the last one here, okay, this ventricle, wait, are there any neurons there around ventricle? It's just CSF, probably that's an artifact. So that's how you do, especially if you don't have a task, a resting state. And for example, if a cell is a built-in toolbox, melodic, it just gives things like that. And then people like looking at it, like, oh, they're trying to find a common pattern to make it like fully automatic. Like in this case, I know like there are arteries going around the midbrain, around the brainstem. This looks like very close to that. And time course is very jumpy, although I haven't sampled enough, but it looks jumpy. And it's probably batch component artifact. And here I see like, in the ventricle, although it's not as high as the other one, well, this is artifact too. And then you flip through another one. This looks like a network. It's just kind of slow fluctuations. It's what we are looking for. So one can classify that. And the straightforward thing will be, okay, maybe there's like frequency dependency on that. It works in certain conditions, but it just, there are like mixed things too. So what you do is like you take the component and then look at the frequency spectrum and see how low is high, how amplitude of low frequency is high with regard to high frequency. So like, we just make a ratio of it. If it's a mixture, if it's that, and then you can classify them. So if there's like low frequencies a lot, then it's a high dynamic range, it's green, okay, this is a network area. Because you don't scan one subject, you might have like hundreds of subjects for a study, you cannot go all over networks too. So this is like an attempt to make it automatize. As I said, there will be a lot of mix. More, how to say, a little elegant, more elegant way to do that is changing the sequence such that, for example, we know that the neuronal activity we are looking for is echo time dependent, which is a property of the bold signal. And then if we change the echo time, we started to see the signal higher. So this, we know that. So instead of acquiring one, we acquire multiple echo times, and then we see this activity is depending on that. And if it is an artifact that is not bold related or like not echo time dependent, then you don't see much difference across different contrasts. Next course, then we'll go through in detail on this. This is called multi-echo API. And you can do classification on that too, quite complicated. Similar to previous one I showed, but it is more quantitative. What you see is like how much this is explained by echo time dependence. If an area is more echo time explained, so it has high value, and then you just go and sort them, and then it creates this kind of an L shape. And all the good components and networks happen to lie on this area, which is shown here, and all the oscillating jumpy areas are as less explained. Is on the end left-hand side of the component spectrum. AFNI has more computational toolbox, PhysioCalc it is called. It is designed to look at those peaks, and if you're familiar with AFNI-ProPy, the way to run it is pretty much similar. It's just few lines of code that is you need to specify the name of the file, is that your cardiac signal is inside and respiratory signal is inside, and the frequency you sample those. So like the biopack frequency in this case. And then you give some other information, like, you know, how fast you measure your image, how many volumes you have. So like, or like if your measurement is like sequential, let's say like, you know, starting from bottom all the way up, interleave up and down. This wants to know that because it wants to correct for that as the physiological signal propagates too. And after you start that, there's a nice interface. We'll let you to go through because it may and it will need a manual correction, because these signals, although I show good signals still here now, it's kind of people breathe in, people sigh, people just, you know, the inside the scanner, these signals are not happen to be always nice. So you need to go through all the peak and troughs in this case. For example, here you see maybe like 100 seconds of nice area, and then and this is like breathing pattern, and suddenly, actually like PhysioCalc is nicely color coding it with the red and blue. Suddenly it's a very long breathing out. Is it an artifact happening? Is it, so you may need to look at it closer. For example, in this case too, like, you know, there's a baseline changing. Is it like subject moving maybe? So you can export those values and look at those values in fMRI data. Maybe there's also motion in that particular time point too. And there's like, if it is too short, it's kind of short blue, like, you know, subject happened to be breathing in and out very fast. Maybe the oxygenation levels in your fMRI data set will change. Hey, if you know that volume number, you can go ahead and look if there's activity is happening there. Maybe you shouldn't rely on that because it's kind of a outlier. This is an example from a literature. So the respiration volume is I showed them previously with the high resolution fMRI is changing a lot and spread all over the brain. You can remove that effect. And if you remove that effect, the network started to be more confined. But in this study, they say, if it's, okay, it's more confined, you remove that effect, but then it's like subject to this scan-to-scan reliability is getting lower. It's kind of interesting thing, like, you know, because what you expect is if you remove the physiology, you expect your signal to be more reliable. But in this case, I think you also remove a little bit your signal too. So, but spatially it becomes more confined and more localized. And there's other thing, as I say, vasculature. In this case, like regions, let's say, prone to CO2. Like, and if you look at the activity patterns, it is auditory and visual areas. And these areas are not only vasculature, these are highly specialized areas that the sensory areas that we're communicating with the outer world. These neurons are highly myelinated. These areas are different in cytoarchitectonic, and one of the thing is like maybe okay, we cannot call this artifact because like this area is active vascular and all this neuronal organization plus vasculature maybe developmentally together, so that removing that area is actually removing the signal. And one clever way, which is actually what I also like a lot, so very recent study from Bright Lab, you can have a physiological task. That we should have thought about that earlier. And then if you have a physiological task that is different in time, so you have multiple tasks you need to do inside the scanner. So you have a working memory, you have a visual task, and you have a mask that you inhale CO2. And these are in time different. And if you do that, you start to see networks appear to be similar, or in other words, spatially overlapping. On the left, you see a working memory task, these areas, but on the right, you see an activity that is CO2 related. And there's like a huge amount of overlap. And similar with visual and also in visual areas too. So I'm approaching the end of this, and I have some take-home messages. So probably you won't be you will be hearing this multiple times throughout this lecture series. Or we need to look at our data all the time, because if you have hundreds of subjects, and then if you just apply the same pipeline, we shouldn't expect that all could come out as the way it should, because there's like a lot of things can happen wrong inside the scanner. And I see that, and I increase that. Always acquire physiology. It never hurts. If you acquire physiology, it's always plus. And then at least you know in different measurement techniques something happened, so you can cross-check with the signals. As part of the question, physiological confounds might be both noise or signal. At this point, it is hard to say, or depending on what you're studying, take it as a grain of salt. So no answer, is it noise or a signal? So it's a confound. It's something we find. It's the nature of the measurement technique, and maybe in certain brain areas we shouldn't remove. It's still a going debate, and most powerfully, like, we should design a task paradigm. Like, before starting a study, if we design cleverly, we can just mitigate and those artifacts, and then just design such that they're different in space or time. And also design a proper processing pipeline that knows all these weaknesses and strengths, and also where to look, the brain area, and all the frequency spectrum that it needs, if it's a fast sequence, to delineate the activity. With that, I'll take your attention, and I'm happy to discuss anything you might have. Thank you.
That's good talk. I'm still wondering, in the resting state, how can you differentiate physiological? I mean, from the signal from Confounds have changed, became the under the real connectivity, what we want. How can you differentiate this two?
I mean, connectivity is. Let me repeat the question. I'm not sure if the audience here, how you understand the physiological changes and how it influences connectivity in resting state. I mean, in resting state, there's no task, so ongoing signals are also model-free oscillating, and it could be in the range in high frequency that could be overlapping with physiology too. So it's a hard task on that, say, but if we are working on bold fMRI, so there is a way to do that. Most of the activity is in the low frequency range, so you can do frequency filtering on that. But there are like transient interactions, of course. But if you're talking about connectivity, that's something else, because two regions might be connected, both physiologically and neuronally. But correlation value is also dependent on the frequency too. So if something is changing high frequency, the correlation value tends to be lower because of the nature of the probability. Things are changing more high frequency. So in that way, maybe that will shift the things in the different correlation values, so you can work on the threshold, but then brings us a problem of the threshold. So yeah, it's a task. especially in resting state, there's no well-known baseline. People usually scan very, very long to understand the signals, how they interact, how much they interact. A long scanning is a part of it, but it still doesn't answer your question fully. Anything more? Any questions or? Sure.
Have there been any studies done on the those area that coordinates with taste in terms of using the capabilities of functional MRI? I'm sure there is, I'm just not familiar. This is all, and I guess when you said noise and I thought that, what was that? What are some of the things that, I mean, physiologically, you have your other structures that can be potential noise, right? I mean, your back of the nerve, that's if you consider that as a canary or a voice.
Yeah.
And they studied that using functional MRI already and published.
For the taste, you said?
Yeah, or taste or smell.
Taste or smell?
Yeah.
Yeah, so those areas, especially smell, those areas are close to areas that are pulsations in vasculature. So those areas are very hard to measure. So you need to have a proper protocol. Either like you just have a restricted field of view in that area and sample that area as high as possible. So you know, probably as high resolution as possible too. So you see the veins and then there's no partial voluming. And then you're just working on the gray matter. Is it olfactory bulb or is it like brainstem, midbrain, subcortical areas? These areas are far from measurements like coils too. So the signal quality is very low there. So one can design a protocol such that to have a decent quality of signal at first, that we can see those pulsations and neuronal activity at the first sight. I mean, if not, everything will be more mixed in the noise level.
Yeah,
in that area.
That's one of the things that we're focusing on, because we partnered with functional MRI. While studying that part.
Yeah.
I'm just procuring the latest research on lactometer and gasometer that can understand.
Yeah.
What that specific thing that would look like. We don't know a lot yet, but we are interested in studying. So
I mean,
brings about, maybe you could lead into another study.
Correct.
Really, but in the real map of the actual odorants that you subject your patient to using the functional MRI and the standard.
Yeah. I mean, in general, subcortical areas are very hard to study because like the nature of MRI, the coils around the brain are working like a near field antennas. So they're just sensitive to the proximities. And the midbrain, as you appreciate, is the furthest point to the antennas that around the brain. So the signal quality in the midbrain is very low. There are a few studies, they try to insert a coil element inside the mouth, which is kind of close to the those areas, but then the coil itself moves because there's like involuntary motion of mouth and the tongue. So it's a task to get a good signal there. But high field might be an answer on that. There are very promising high field studies in 7 Tesla, good amount of activity detected in the midbrain and brainstem.
I feel that we have it here.
Exactly.
Right.
Exactly.
One of the three in the world, I think.
Correct.
That's great.
I feel 70.
70 or higher.
Well, Harry would be good.
Let me look at the chat.
70 would be,
70 would be more doable.
yeah. More people would prefer you.
That's good.
Oh, is it down? Meeting is down?
No, I still. Thank you.
Any questions in the chat? Oh, there, yes. Oh, okay, that was just beginning. All right. That's it, I guess.
Thank you so much.
Thanks for your interest. All right.